In this video lecture, I will show you step by step how to design a synchronous counter. Before that, what do you mean by counter? So counter is a sequential circuit which counts the number of clock pulses applied at its clock input. The counters are of two types. One is asynchronous counter, which is also called as ripple counter, and second one is synchronous counter. In asynchronous counter, the clock is fed to the first flip-flop and rest of the flip-flops get the clock from the output of a previous flip-flop. That's why it is called as a ripple counter. In synchronous counter, all flip-flops are clocked simultaneously. So we'll mainly focus on synchronous counter. So all the flip-flops are clocked simultaneously, and that's why it is also called as a parallel counter. Now it has no ripple effect, therefore it has less propagation delay as compared to asynchronous counter. And as it is having less propagation delay, it is comparatively faster than the asynchronous counter. Let us go through the steps for designing a synchronous counter. The first step is find the number of flip-flops required. How many flip-flops you are going to require in order to design a synchronous counter, you have to find out first. In the second step, you have to write down the count sequence in the form of truth table. In the third step, you have to select the flip-flop and draw the excitation table. Select the flip-flop means there are different types of flip-flop like D flip-flop, T flip-flop, JK flip-flop, SR flip-flop. Out of them, which flip-flop you are going to use in your design, you have to first select that flip-flop, and then accordingly you have to draw the excitation table. Use that excitation table, and depending on that you have to find out the expression of flip-flop input by the help of K-map. And once you find the expression, in the last step you have to draw the logic diagram. So we will go through them one by one. In step 1, we have to design a 4-bit synchronous counter. So in step 1, I have to find out how many flip-flops are required to design a 4-bit synchronous counter. The answer is very easy because number of bits are 4. Each flip-flop is capable of storing 1 bit. So to design a 4-bit counter, I will require 4 flip-flops. Now, in the second step, what you have to do? You have to write the count sequence in the form of truth table. The first, we will write the count sequence in the form of state diagram. So what is state diagram? The state diagram looks like this. We are going to start from the initial state, which is 0, 0, 0, 0. From 0, 0, 0, if one clock pulse is applied, it will go to the next state, and it is obviously 0, 0, 0, 1. One more clock pulse is applied, so it will go from 0, 0, 0, 0, 1 to 0, 0, 1, 0. That is state 1 to state. Likewise, with each passing clock, it will go through these 16 states. The last state is 1, 1, 1, 1, which is equivalent to 15, because even if it is a 4-bit counter, it starts with 0 and ends at 15. So total 16 states are there. And after 1, 1, 1, 1, it again goes to its initial state. So from this state diagram, we will form a table where a previous state is written and next state is written. In the first sense, this is the previous state and this is the next state. After first clock, this is the previous state and this is the next state. And this happens in a sequential manner. So the same state diagram is converted into this truth table. So 0, 0, 0 is the present state. After application of one clock, it is converted into 0, 0, 0, 1, that is the next state. After second clock, 0, 0, 0, 1 is transformed into 0, 0, 1, 0. Then after third clock, 0, 0, 1, 0, that is 2, gets converted into 3. Likewise, 3 gets converted into 4. State 4 goes to state 5, state 5 to state 6, state 6 to state 7, state 7 to state 8, state 8 to state 9, state 9 to state 10, state 10 is followed by state 11, state 11 is followed by state 12, state 12 is followed by state 13, state 13, that is 1101, is followed by 1110, which is 14. State 14 is followed by state 15, and state 15, that is 1111, is followed by the initial state, that is 0000. So this is the truth table showing how present state is converted into next state. Now in step 3, what we have to do? We have to select the flip-flop and draw the excitation table. Now I will go for T flip-flop. You can go for JK flip-flop also. So I will go for T flip-flop. And for that, I should know the excitation table of T flip-flop. Now what is excitation table of a flip-flop? Excitation table means the table which shows what input you should apply to the T flip-flop so as to make the transition from present state to next state. Here Qn represent present state, Qn plus 1 represent next state. So when Qn is 0 means present state is 0, and that 0 goes to the next state and the same 0 is retained, in that case the value of T should be 0. If present state is 0 and after 1 clock it goes to the next state 1, then in that case the T input of the flip-flop should be given 1, so that 0 to 1 transition takes place. In order to make transition from 1 to 0, T input should be 1, and in order to make transition from 1 to 1, T input should be 0. So what input should be applied to the T input of a T flip-flop, that is shown in this excitation table. A simple way to remember the excitation table of T flip-flop is that if you carefully observe it, you can guess that the present state and next state, when these two states are same, means there is no change, in that case value of T is 0. So 0, 0, both states are same, so value of T is 0. Here also present state is 1, next state is 1, so there is no change, so value of T is 0. T stands for toggling, means no toggling is taking place in first state as well as last, so value of T is 0. In second row, T 0 is changed to 1, so toggling is taking place, so value of T is 1. In third row, 1 is transformed into 0, so again toggling is taking place, so value of T is 1. In short, if there is no change, value of T is 0. If there is a change in present state and next state, value of T is 1. And the same knowledge we will be using in order to form the excitation table. So these tables we have already seen that 16 different states of present state are converted into 16 different next states, and the knowledge of this excitation table of T flip-flop is taken care while designing the counter. So this table shows that how to find out the values of TD, means what should be the input of T flip-flop so as to convert this QD into QD1 plus 1. QD is the present state and QD1 plus 1 is the next state. Now look at the first row. 0 is converted into 0. So there is a no transition or no change. So value of TD is 0. In second row, 0 is the present state. Next state is also 0. So again there is no change. So value of T is 0. In third row, same is the case. So TD is 0. In fourth row, same is the case. So value of TD is 0. Next row, same is the case. So value of TD is 0. In the next row, 0 is converted into 0. So again value of TD is 0. In next row, this 0 is converted into 0. So again the value of TD is 0. In the next row, 0 is to be converted into 1. So there is a change, and that's why the value of TD is 1. In next row, 1 is to be converted into 1. So again no change. So value of TD is 0. Same is the case with next row. 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 Again 1 is converted into 1. So TD is 0. Again 1 is converted into 1. TD is 0. And what about the last row? 1 is converted into 0. So there is a change or there is a toggling. That's why the value of TD is 1. So you have found out the values of TD for QD as a present state and QD1 plus as a next state. So we have calculated one set. Now what is the next step? We have to find out the values for TC. TC correspond to QC and QC1 plus 1. We are going to use the same logic. So we'll take the help of excitation table of T flip-flop. So 0 is the present state, 0 is the next state. So there is no transition. So 0, 0. So what should be the value of T? T should be 0. So value of TC is 0. Again 0 is the present state, next state is 0. No change. So TC is 0. Same is the case with next row. In the fourth row, 0 is transformed into 1. So definitely there is change. So 0 to 1, value of T should be 1. Hence TC is 1. In the next row, 1 is converted into 1. So 0 is the value of TD. Again 1 is converted to 1. The value of TC is again 0. 1 is converted to 1. Again the value of TC is 0. Here 1 is converted into 0. 1 is the present state, 0 is the next state. Hence value of TD is 1. In the next row, 0 is kept as it is. So TC is 0. 0 is kept as it is. So TC is 0. In the next row, present state is 0. Next state is also 0. So value of TC is 0. In the next row, present state is 0 and next state is 1. That's why T is equal to 1. Because 0 to 1 transition, T should be 1. In the next row, 1 is there. So value of TD is 0. Same is the case with next row. And in the last row, 1 is converted into 0. That's why toggling is taking place. So for 1, 0, value of T should be 1. So from excitation table, we have calculated 16 different values of TC. Now what is the next step? Obviously, we have to find out the value of TB. So value of TB is found from the knowledge of QB and QB plus 1. QB is the present state, QB plus 1 is the next state. And as we have already calculated the value of TD and TC, from that knowledge, we will easily calculate the values of TB, which I have directly shown here. And the last step is to calculate the values of TA. For TA, we need the help of QA as a present state and QA plus 1 as a next state, and they are also calculated in the same fashion. So we are done with calculating the values of TD, TC, TB, TA, and they are shown here. Now what is the next thing I have to do? I have to find out the expression with the help of K-map, and for that I will take the help of present state and the inputs of flip-flop. So for each input, one K-map will be there. So for TD, one K-map will be there. For TC, one K-map will be there. For TB, one K-map will be there. And for TA, one K-map will. So in total, I will have 4 different K-maps. And I will take present states, because next states are not going to be taken into account, because they will appear when I apply these inputs. So in order to generate next step, I have to take the help of present state. So what are various possible combinations? 0, 0, 0, 0 to 1, 1, 1, 1. So in total, 16 possible combinations are there. So I will require the K-map of size 16 cells. So use the K-map and find the expression for the flip-flop input, that is step number 4. So again, I have drawn the same table here, and one by one I will draw the K-map for each input. So first we will go for the K-map to find the expression for TD. So this is the K-map. The inputs are QD, QC, QB, QA, that is these 4 are the inputs, and as 4 inputs are there, obviously it will have 16 different cells. So these cells are numbered as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. These cell numbers correspond to decimal equivalent of these 4 numbers. So 0000 means 0 in decimal, that correspond to this cell. 0001 correspond to 1 in decimal, so it correspond to this cell. 0010 correspond to 2, so it correspond to this cell. Likewise 1111, which is equal to 15 in decimal, so it correspond to this cell. So these 16 different values under TD, they are written in these 16 cells ranging from 0 to 15. Now, where to write the values? So you will find that 1 is in this cell, and this is cell number 4 plus 2 plus 1, cell number 7. Similarly, 1 is in the last cell is cell number 15. So cell number 7 and cell number 15 contains 1. So cell number 7 is filled with 1, cell number 15 is filled with 1, and remaining cells are 0. So, or I have kept them empty also. Now I can form a pair of 1 1. Now I have to find out the expression. Now look at the left hand side, 0 1 and 1 1. So 1 is common, and this 1 correspond to QC. Now look at the column. So 1 1 is the column heading. So 1 1 correspond to QB and QA. So the expression will be QC from row and QB QA from column. So TD is equal to QC QB QA. So once I have found out the expression of TD, now the next step is I will go for the design of K-map for TC. So I will design the K-map for TC. In case of TC, 1 is written in cell number 3. Similarly, next one correspond to cell number 7. Next one correspond to cell number 8 plus 2 plus 1, that is 11, and the next one correspond to cell number 15. So cell number 3, cell number 7, cell number 11 and cell number 15, they are filled with these 4 ones, and rest of the cells contain 0. So I can form one chord out of this. So these 4 ones are grouped together, and as they occupy entire column, I will just look at the column section. So column is 1 1. 1 1 means 1 is QB and this one is QA. So the expression for TC will be obviously QB into QA. Now what is the next step? I will form the K-map for TB. So K-map for TB will be formed. Now where is 1? 1 is here, that is cell number 1. Cell number 3 also has 1. Cell number 5, cell number 7, cell number 9, cell number 11, cell number 13 and cell number 15. So 1, 3, 5, 7, 9, 11, 13 and 15. These 8 cells has 1 and remaining cells have 0. Now as there are 8 ones, I can form one octet. So I will form the group of 8 ones. Now as they are occupying the whole columns, that is column number 2 and column number 3, there is no need to go for the row. We will just concentrate on the column. This column as well as this column. In this column, the second bit is common. This one is here and this one is also here. So we will take into consideration only this second variable, that is QA. So what is the equivalent of TB? TB correspond to QA. So the expression for TB is QA. And finally, we will design a K-map for TA. So in case of TA, if you look carefully, you will find that all the values under TA are 1. So there are 16 1. So this K-map has all ones into it. And when all the cells of a particular K-map are filled with 1, the expression is always 1. Expression is always 1. So value of TA is 1. So what I have done? I have found out the expression for TD, TC, TB, TA with the help of K-map and with the help of present state of the flip-flop. Now the last step, I have to draw the logic diagram. And for logic diagram, I will take the help of the 4 expressions from 4 K-maps which I have just designed. TA is equal to 1, TB is equal to QA, TC is equal to QB into QA, TD is equal to QC into QB into QA, Now let us design it. So T flip-flops are required. Total 4 T flip-flops are required. They are flip-flop A, flip-flop B, flip-flop C, flip-flop D. D represents MSB and flip-flop A represents LSB. Remember this. Now we are designing synchronous counter. So clock of each flip-flop should be common. The source of clock is common. So all the clock signals, they are connected together and a common clock is applied to them. What is the next step? I have to have TA as a 1. TA is the input of flip-flop A and it should be given logic 1. So TA, that is input of flip-flop A, it is connected to logic 1. So I have done with this expression. What about TB? TB is the input of second flip-flop and its value is QA. What is QA? QA is the output of first flip-flop. So QA is the output of first flip-flop. It is connected to TB, which is input of second flip-flop. That's why TB is equal to QA. Now what about the next expression? TC. TC means the input of third flip-flop. What's its value? Its value is QB into QA. QB into QA means there is a ANDing operation between QB and QA. So we will require the help of one AND gate. So a AND gate whose inputs are QA, this is QA, QB is given as a second input of AND gate and obviously its output will be QB QA and its output is given to the TC. So TC is QB into QA. TC is QB into QA. Now what about the TD? TD is QC QB QA, means it is the AND of QC QB and QA, but we have already obtained QB and QA. So I will require one AND gate and this expression QB QA will be ANDed with QC. So QB QA is given as a first input to this AND gate and second input is QC. So obviously its output will be QC QB, that is the first input, and QB QA, that is the first input, and QC as the second input. So output of this AND gate will be QC QB QA and it is to be given to QD. And what is the output of last flip-flop? QD. QD is the output of last flip-flop. So in this way we have designed a 4-bit synchronous counter. Hope you have understood it. Thank you.